So when we said a mole earlier in this chapter, so we said a mole is like a dozen. 1 dozen equals 12. 12 what? Of anything, right? And so that's why I said a mole is a little different than how we think about units of measure. Like 12 inches can't be a certain number of feet of anything, right? 12 inches is always 1 foot. And so this feels a little different from a unit of measure, but a mole is more like this idea of a dozen. So 1 mole equals 6.02 times 10 to the 23 of anything, right? So like I said, you could have a mole of donuts. I said that off camera, so if you guys are watching this on camera, you're like, when did he say that? I said that off camera, right? But we said you could have a mole of donuts. It would just be a whole bunch of donuts, right? That's like donuts for life. Actually, they'd be stale in a week, and you wouldn't want those donuts, so you're throwing away a lot of donuts if you have 6.02 times 10 to the 23. But you could say that if you had that many donuts. You have a mole of donuts, right? One of the things I said in the video, the previous video, was that Mole Day, we celebrate it on October the 23rd from 6:02 a.m. to 6:02 p.m., right? And that's how we remember, one way that we remember that, and we honor this idea of the mole. And so I always encourage my students to dress up like a mole and party from 6:02 a.m. to 6:02 p.m., doing various chemical reactions and just to celebrate Mole Day. And I did mention in the last video that I'm always looking for a mole costume. I've never found a mole costume, but if you guys find one, definitely class participation credit if you can track down a mole costume for me to wear to school on Mole Day, all right? So mole's just not a popular thing. Like, I'm always thinking like every Halloween, surely there's like some bargain mole costume somewhere, but people just don't dress up like moles, it's not very popular. So
check it, the 23rd is a Wednesday.
23rd is a Wednesday this year?
Yeah,
so I'd be wearing it to Bible class. I'm just going to make my own mole costume, I guess. So anyway, one of the things that we said then is, if you guys remember if you have watched the other video, if you've already watched it, what we said was that the periodic table, now that we are aware of this concept of a mole, the periodic table tells us a couple of things. Like if we looked at carbon, for example, if I look at the periodic table, carbon looks like this, right? And we said previously that this number right here, this is our review so far, this number right here, 12.01, means what? What do we know previously that means? Okay, that means that's the mass in AMU of one carbon atom, right? So 12.01 means for carbon. It means the mass in atomic mass units of a single carbon atom. And number 2, what we've just learned in this chapter is it also means it's also the number of grams. Let's see. The mass in grams of 1 mole of carbon. All right. So what do we mean by that? We mean if we had 6.02 times 10 to the 23 carbon atoms, they would have a mass of 12.01 grams. Or in other words, so i.e., 1 mole of carbon equals 12.01 grams. Again, of carbon. And so the reason we use this mole idea is because the because atoms are incredibly small, right? Molecules are incredibly small, and we don't want to be saying, if we're counting the number of molecules or atoms that we have, we don't want to have to use scientific notation every time we do that. But we would have to if we were using values that we were familiar with, right? So we come up with this new unit, a mole, that's equal to that. And so this is the important thing that you need to be able to take away from the periodic table. This idea here we're going to use over and over again. You're going to go to the periodic table and you're going to go, nitrogen has an atomic mass of 14.01, and so that means that 1 mole of nitrogen atoms will be equal to 14.01 grams, right? And so it's important that you get that down. It's, again, one of those things we're going to use the rest of the course, okay? So super important that we understand that. What it also means, again, this is just review. What it also means is that because mass is additive, right? We did an experiment last time that you guys messed up, where we were trying to show that volume is not additive, but that mass is additive, right? And because mass is additive, that means that, let's say we have carbon, right, which looks like that, and we also have hydrogen, which looks like this, right? And if I want to know what the mass is of 1 mole of methane, which is CH4, I could go to the periodic table and I could say, well, because I know that 1 mole of carbon equals 12.01 grams of carbon, right? And because I know that 1 mole of H, of hydrogen, equals 1.01 grams of hydrogen, then I can apply that rule to, I can add these together. In CH4, I've got 1 carbon atom, right? So looking at the periodic table, that's going to be 1 times 12.01 plus, I've got 4 hydrogen atoms, so 4 times 1.01. If I add all of that up there, it's 12.01 plus 4.04. That's going to be 16.05. Right? In atomic mass units, that would be the atomic mass of CH4. Right? Just adding up the individual atomic mass of all of the atoms would give me this value. But because that's true, it also means that 1 mole then of CH4 is going to have an atomic mass, not an atomic mass, it's going to have a molar mass, what we call a molar mass, of 16.05 grams. And again, we can do that because mass is additive. So we could do this mole idea for individual atoms, like we did a second ago, or we could do it for molecules as well, right? We just add it all up. And like I said, what we call this value here is the molar mass. In other words, the mass of 1 mole of that stuff. Whereas right here, we call this the atomic mass. That's the atomic mass of CH4. This is the molar mass of CH4. Okay? And eventually, once we get good at this, you're going to just see me do this math here, and I'll skip writing down this AMU step. I'll just go straight to this step, and I'll just write down that when we add these values up here, it means that we have a molar mass of 16.05 grams per mole. Right? Because every mole has that many grams in it. So this is another way you might see the molar mass written. Any questions for me about that? Does that make sense? It's new, right? It's like, I've never heard of mole before. But think about doing this exact same thing with a dozen, right? If I told you I had 36 donuts, you'd have no trouble going, well, that's 3 dozen, right? And it's really the same thing at the end of the day here. But getting this trick down, understanding and knowing that this number represents the molar mass in grams is really the key takeaway from using our periodic table to figure all of this out. So it may be a little confusing at this point, but the repetition of it, you're gonna get to a point where it's like, okay, I got it. It's no big deal. All right. Now, one of the things that I did not go over on the last video is I'm just gonna mention this. It's the term hygroscopic, and some chemicals are very hygroscopic, and all that means is that those chemicals readily absorb moisture, particularly water. And so I just want you to be aware of this in case you ever see this on a bottle for some chemical substance. Sometimes you'll see that chemical substance and it'll be like, I don't know, did they give an example in the book? Let's see. Like you'll see that some chemical compound mentioned, and then you'll see dot, and you might see something like 5H2O. And what it means is that every molecule of this substance here, in the container that you're pouring this stuff out of, every molecule is combined with 5 molecules of water, because it's a hygroscopic material. So it just means, I just want you to know that. I just want you to know that vocabulary word, right? Know the definition of that. It just means readily absorbs moisture. Particularly water. Like I said, that's usually where you see it on in a lab if you're grabbing a particular chemical. It'll list it like that. All right, so the next thing that I want to talk about, and I'm trying to get us to a point where we can do our experiment today. But this is the other big takeaway from this chapter, is that if you have a chemical equation like this, so we've got N2 plus 3H2, and that's going to combine together to make 2NH3, which is ammonia. All right, so this is what type of reaction? If I'd given you this on the test that you just took, what would you have said what kind of reaction would you have picked this as? Formation, right? Because you've got a single substance over here. You're forming that substance. If it had been reversed and the single substance had been on the left side, it would have been a decomposition reaction, right? You're decomposing it into its individual components. So we're forming ammonia here. This is the formation of ammonia. And so what we've learned up to this point is that there's an understood 1 here, right? In front of the N2. And what we would say, based on our knowledge so far, is we would say if you take 1 nitrogen molecule, why did I say molecule and not atom? You guys take your time. I wanted to swallow coffee anyway, so plenty of time. What's the difference between a molecule and an atom? Because there's 2 of them, right? An atom is just a single one all by itself. As soon as it's bound, as soon as you have 2 or more atoms bound together, it becomes a molecule, right? So it's totally true that I've got 1 molecule of nitrogen plus 3 molecules of hydrogen that combine together to form 2 ammonia molecules, okay? Up to this point, that's what you guys would have said those big numbers in the front meant. You would have said that means that's how many molecules we have, right? Which is true, all right? But here's the thing. Molecules are incredibly small, right? So we're never in the lab going, I'm going to take one nitrogen molecule, right? I'm going to get my little tiny tweezers and I'm going to combine it together with 3 hydrogen molecules. I'm going to put those together and I'm going to make exactly 2 molecules of ammonia, right? We never do a reaction like that. That's too tiny. So what did I say? What's our new unit that we have? Because we're dealing with things that are so small that we use to think about the number of these that we have. What's our new unit? A mole, right? So from this point on, the way that we're going to think about this is we're going to think of this as 1 mole of nitrogen molecules, okay? If I have 1 mole of nitrogen and I add it to 3 moles of hydrogen, I'm going to get 2 moles of NH3, all right? So that's the other big takeaway from this chapter. And the first big takeaway was we can use the periodic table to figure out how many grams are in a mole. And the next big takeaway is that this chemical equation, which I said functions like a recipe, we can look at these big numbers in the front and consider those to be moles instead of simply molecules, all right? So what that means is, again, the recipe for this is if I want to make 2 moles of NH3, I need to have 1 mole of N2 and 3 moles of H2, okay? Questions about that? That highlights even more the fact that this functions like a dozen, right? Because it would be also true, since these are molecules, I could say if I had 1 dozen N2 molecules and 3 dozen H2 molecules, I could make 2 dozen NH3 molecules, right? So I could plug mole in there as well. So what we call these big numbers in the front here, do you guys remember what this chapter, what the complicated sounding word was that we said this chapter was about if you've started the video? Stoichiometry, right? So we're going to call these numbers in the front the stoichiometric coefficients. All right, you know how in algebra, right, if you had an equation like this, y equals 3x squared plus 2x minus 1, right? We called these numbers that are in the front of our variable, we called these coefficients. So we're going to use the same term here, but because they represent the number of moles, we call them the stoichiometric coefficient, all right? So that again is just a term I might, if I throw it out there, if I mention the stoichiometric coefficient, that's what I'm talking about, the big numbers in the front in the chemical equation, okay? All right, let's see. So where do we go from here? So what this means, again, thinking back to our recipe idea, all right? If we think of this as a recipe for making ammonia, in this case, right? And just like going back to our brownie recipe, right? If I have 1 bag of mix, 1 bag of mix plus 2 eggs plus 1 cup of water. This recipe changes every time I write it down. I don't know what the actual brownie recipe is. And it makes 12 brownies, let's just say, all right? This tells me the relationship between each of these things in this recipe, right? If I told you, if you knew this was the recipe for making the 12 brownies, right? And I told you, hey, I'm going to do the brownie recipe using 4 eggs instead of 2, then you're thinking he must be making how many brownies then? If I told you I'm doing the recipe and I need 4 eggs for it. 24. It's okay, it's all right. We'll edit that out of the video. So twice as many eggs, so I must be making twice as many brownies, right? 24 brownies. And so the point is, I can look at this and go, well, if I'm using one bag of mix is going to give me 12 brownies, right? Simple enough. But if I'm using 2 bags of mix, I don't know why I can't spell bag this morning. I'm making 24 brownies because 12 times 2 is 24. If I use 3 bags, right, I've got 36 brownies and so on, right? Well, the same thing works with these chemical equations, all right? Because this chemical equation is true, see how like here I was able to say this? And I could use this fact in conversion relationships, right? If I said, hey, I don't want to make 12 brownies, I want to make 48 brownies, and I said, how many bags of mix would I need? Then you could say, oh, I'm going to take this and I'm going to multiply it by, I'm going to put the number of bags on top, because this is my conversion relationship right here, right? I put the bags of mix on the top, I put the number of brownies on the bottom, right? I do the math with that. 12 goes into 48 4 times. My brownie units cancel out. I've got 4 bags of mix that I need in order to make that many brownies, right? By the way, did you guys, if you haven't watched the whole video yet, you probably haven't seen me do this, but I'm going to start doing these conversions. I told you guys we're doing conversions over and over and over again in this class. I'm going to start writing them like this. Like instead of saying multiplied together, I'm going to do it kind of in this table format. And the reason why is because these conversions are going to get longer. And so we're going to do like this first set of multiplication and division, and then we have to do a second set and so on. So if you see this, it's just saying this number here times this ratio right here, okay? Just another way to write that and keep it a little better organized. So we're going to do the same thing with our mole relationships now, right? Because we, just like one bag produced 12 brownies, I can say, well, that means based on this recipe that 1 mole of N2 will produce 2 moles of NH3. And now I've got a conversion relationship I can use, right? And I can also say that 3 moles of H2 will produce 2 moles of NH3. Okay? Just like another one I could have written down from my brownie recipe that was that 2 eggs equals 12 brownies. Does that make sense to you guys? I feel like the recipe thing's the easiest way to kind of get your head around what's happening here. It's the same exact idea, right? Really, the only difference is we're using this wacky unit called a mole that we're not familiar with, right? It's new to us. But everything else, the idea, all the other ideas are the same. I don't think they're going to say this in this chapter. I think this is a concept they're going to introduce in the next chapter. But it also means that we can say, well, if I have 1 mole, if I'm following this recipe right here, and I have 1 mole of N2, how many moles of H2 am I going to need? Following this recipe. Think back to the brownie thing. If I have 1 bag of mix, how many eggs am I going to need? 2. So if I have 1 mole of N2, then I'm going to need 3 moles of H2. Right? I'm just taking the big numbers from the equation here. So all of these relationships are true for this balanced chemical equation. And I can use any of these relationships to convert from one to the other if I change those numbers. Okay? So you guys see where I got these from? Just taking the big numbers in the front and saying these are all equal to one another because these big numbers in the front are true, since this is a balanced chemical equation. So let's apply this to a problem. This is 7.4 in the book. 2H2O, 2H2O2 is going to be broken down, decomposed into 2H2O plus, what is it?
It's just staying straight.
What happened? Whoops. Wait a minute, what were you telling me? What were you telling me just happened?
So it's not moving.
Oh, was it? Has it been? Oh man, bummer. Okay. Yeah, I didn't have human tracking turned on. Thank you. I thought it was blue earlier. Blue means it's tracking me. Okay, that's okay. It was pointed at the board, so I think we got all that. It's just you're gonna not see my head in some of the shots. All right, so we're doing, this is example 7.2 in the book. Not 7.4, not 7.2. Example 7.4. And we're decomposing hydrogen peroxide. That's what H2O2 is, okay? 2H2O plus O2. And remember, there's an understood 1 in front of O2. So this means, now that we know a new meaning for these numbers in the front, we would say this means that 2 moles of hydrogen peroxide will break down into 2 moles of water and 1 mole of oxygen. Okay? Make sense? So then the question is, how many moles of oxygen and water can be made if we start with 12.18 moles of H2O2? So how much water and oxygen will I get if I'm breaking down this many moles of hydrogen peroxide? Okay? So let's do the same thing that we did with my example just a second ago. And let's write down the relationships that we know from this chemical equation. There are 3, just like we had from our last example, right? What are the relationships that I can write down, the molar relationships that I can write down between the substances in this chemical equation? Give me one. I can say this thing equals this thing, right? I'm writing down conversion relationships based on the number of moles. See if you guys are following me. Anything? 2 what of H2O? 2 moles. 2 moles of H2O. Right? 2 moles of H2O2. Whoops. Equals 2 moles of H2O. Right? 2 here, 2 there. All right? Give me another one, Daniel. What else is true? Bryson's given us one.
Say like, can you like switch it around and say like 1 mole of
I'm taking this directly from the big numbers, the stoichiometric coefficients in my chemical equation. And because there are 3 substances in here, I should be able to write down 3 relationships. Can you give me another one, Ella?
Would it be 2 moles of H2O2 equals 2 moles of O2?
2?
Or sorry, 1.
1 mole, right? Because this one hasn't understood. 1 in the front, right? 1 mole of O2. Good. So there's a second relationship I can write down, right? There's one more. What's the last one? Do you know, Daniel? That I'm just pulling directly from my balanced chemical equation here. There's one other. I've seen how H2O2 and H2O are related. I've seen how H2O2 and O2 are related. The one thing I haven't seen is how does this chemical equation tell me that H2O and O2 are related?
So it would be 2 mole H2O2.
No, not H2O2. We've got the relationship with all of these. I want to know, how are H2O and O2 related? 2 moles of H2O is equal to what?
Is
Yeah. Of O2, right? I'm just grabbing my numbers from there. See how easy that is? Because this recipe stands, because this chemical reaction is true, then I can say all of these things are true. And the reason I want to be able to say those things are true is so that I can do this. So that if in the lab I'm not breaking down 2 moles of H2O2, I happen to be breaking down 12.18 moles of H2O2, I want to know how much water and how much oxygen I can expect to be produced. Okay? That's what they asked us. So at this point, guys, I just want you to see, again, at this point, it's just conversions. It's just unit conversions is all we're doing, all right? We're converting, they want to know how many moles of water are going to be produced and O2. That's their question, right? And so all we're doing is we're starting with 12.18 moles of H2O2, and we want to convert that to the number of moles of H2O. And then we're going to start with 12.18 moles of H2O2, and we convert that to the number of moles of O2. Okay? Now, what am I multiplying this guy by so that I'll get the number of moles of H2O? Which of these 3 conversion relationships do I need in order to do that? Relationship 1, 2, or 3? Let me write this down. All right. Let's say I put these 2 things, these 2 conversion relationships on the board. All right. And I said, hey guys, we need to convert 3,600 seconds to the number of minutes. Which conversion relationship would you choose? This first one or this second one? The second one. Why? Because it's got seconds and minutes in it, right? So if I'm asking you, hey guys, I need to pick one of these and I need to convert from moles of H2O2 to moles of H2O, then you're going to have to pick the conversion relationship that has H2O2 and H2O in it, right? Which one is that?
The first one.
The first one, right? So which one goes on top, right? We know these 2 things are equivalent. We put one on the top and one on the bottom. Which one goes on the top? If we're converting 2 moles of H2O.
The 2 mole H2O would be on top.
This goes on top, right? Because that's the unit we want to end up with. This goes on the bottom because that's the unit we want to cancel out. And so that's why it's really important when we write down moles, you put moles of what? So you can make sure your units are going to cancel out, right? I can see very clearly my units are going to cancel out there. In this case here, because we have 2 over 2, right, which is just 1, the number's going to be the same. So 12.18 moles of H2O. Now what about this guy? I want to go from H2O2 to moles of O2. Which relationship am I using? 1, 2, or 3?
It'd be the second one.
The second one, because the second one has H2O2 and O2 in it, right? So we're going to do the same thing. We want to end up with O2, so we put the moles of O2 on top. On the bottom, we put the moles of H2O2. Those units cancel out. And so 12.18 is going to be 1/2. The moles of O2 are going to be 1/2 that of these moles. Right? Remember, the way to think about this is you're saying 12.18 times 1 divided by 2. The number on top you're always multiplying by. The number on the bottom you're always dividing by. So what does this end up being? 6.09? So those are our 2 answers. technically, based on the significant figures, I should put a 0 at the end of that second one there because this one has 4 significant figures. But again, we're not going to sweat that the rest of the class, right? Now, just to make sure, again, make sure that this is clicking with you guys. This should have been obvious to us that right here, the way the recipe works is I have 2 moles of this. I have the same number of moles of this. I have half the number of moles of this. You guys see that? Right? So then if I started with 12.18 moles of this, the number of moles of this would be the same because they both have a 2 in front of them. This one is half the amount of this 2 here, so it should make sense also that we would need half of the O2, right? So it's logical, but you really want to know the mathematical side because sometimes the numbers aren't as easy, right, as these were. So you got to be able to figure out these relationships and be able to write down these conversions. This is so important, so do not let me leave this section if you're confused about anything. You guys are good? Daniel, I feel like you need to ask me a question.
I don't know, I was just kind of confused about like how we, I think I was like writing that as while you were explaining. With just like finding the different combination or like different.
So are you confused about why we were able to write down this, this, and this?
Yes.
Okay. All we did is we just said, we said for every substance in this equation, we just took the big numbers in the front, knowing that that represents moles, and we wrote down relationships between every substance in the equation, all right? So we want to know how is H2O2 related to this? We want to know how is H2O2 related to this? And then we also want to know how these guys are related to one another, okay? And that's everything in the equation. Do you see there's no other relationship we need to know? If we know how these two are related, how these two are related, and how these two are related, we know the relationship between everything. And the way they're related is just the big numbers in the front, right? If we want to see how this and this are related, well, 2 moles of this will make 2 moles of this, which is what this says, okay? 2 moles of this will make 1 mole of this, which is what this says, right? And in this balanced chemical equation, if you have 2 moles of H2O, you will always have 1 mole of O2, which is what this says. So that allows us to just say, this is equal to this is equal to this, and this is equal to this. And then they asked us, they said, we're starting with this many moles of H2O2. We're not starting with 2, like the chemical equation said, we're starting with 12.18. So they said, well, how much of this and how much of this are we going to have? And so that told us that we were converting from moles of H2O2, which is the number they gave us, to moles of H2O. That's what we wanted to end up with. So we used this conversion relationship because this conversion relationship, which is this, had H2O2 and H2O in it. All right? Just like if I told you, again, going back to the brownie recipe, if I said 1 bag plus 2 eggs plus 1 cup of H2O equals 12 brownies, right? If I said, I am going to make this recipe and the version that I'm going to make is going to require 8 eggs, okay? And I want to know how many cups of H2O are needed, okay? You could do that simple math in your head, right? You would say, what? How many cups do I need?
4.
You would say 4, right? But mathematically, what if those numbers were harder? What if I said, I'm going to use 7/3 of eggs? All right, now you've got fractions or decimals or whatever, it gets more complicated, right? What if I said I'm going to use 2.4 eggs? How are you going to figure out how much water you need now? Well, you're going to have to do the math with it. You're not going to be able to do the simple math in your head, right? What is the math that we get from this? Well, what we know from this is we know that 2 eggs will always be equal to 1 cup of H2O because that's our recipe, right? That's the same thing I did here. I said 2H2O will always require 1 O2. And so I wrote that down. Right? And so if I want to convert from eggs, if I want to know if I've got 8 eggs and I want to convert to how much H2O is required. So I got eggs. How many cups of H2O do I need? Then I'm going to say, well, because I know this, I can use that conversion relationship and I can say, put the eggs on the bottom because I want that unit to cancel out. Put the cups of H2O on the top. And when I do this math, I get 4 cups, like you told me. You did it in your head, but you got to know mathematically how to write it down. So if these numbers are more complicated, you can still do it, right? If I said something weird, like I said, 2.4 eggs, right? I just changed this number 8 here to 2.4, and I plug that in my calculator. How many cups do I need? Well, I'll need 1.2 cups of H2O if I'm using 2.4 eggs. Does that help a little bit? Again, the more you do, the easier it's going to be. You're going to have homework problems that let you practice this. We're going to be doing this same thing in chapter 7, and then we're going to do some more complicated ones in chapter 8, but you still have to understand those basic principles. So we're going to be doing this over and over and over again, okay? All right. Now, what if we did, oh, we've already been going an hour and a half, haven't we? We need a break. Let me ask you one more thing, okay? And then we'll take a quick break and then we'll do this lab. Back to my brownie recipe, right here. All right? I want to make as many brownies as I have, but I only have 3 eggs. All right? I've got several boxes of mix. I got plenty of water, but I've only got 3 eggs. What is the max number of brownies that I can make?
So you'd have to like multiply 1 bag times, or like 2 out of 3, or 2 over 3, because like, or like if you only, because that's only, or you multiply everything times 1/2, because you have enough for 1 recipe plus a half a recipe.
Okay. Right. Yeah. 1.5. So I would need 1.5 bags of mix. I'd need 1.5 cups of water, and I can make how many brownies?
18.
18 brownies, right? Why is that? Was it because of how much water I had? I had plenty of water. My fridge will just keep pouring water out, right? Unlimited supply of water. I told you I had a bunch of boxes of brownie mix. What determined the number of brownies I could make was the eggs, because I only had 3 of those, right? And there was an egg shortage. I couldn't even go to the store and buy more, right? My chickens, that's all they produced, 3 eggs, right? I don't really have chickens. So what we call the eggs in that case is we call that the limiting reactant. In other words, the eggs limit how many total you can make, all right? And the same thing happens in chemical reactions. You have a certain substance that's the limiting reactant. You've only got so much of that. You've got excess, you've got plenty of the other stuff, but you only have so much of one, and so that limits the reaction. And so that's what we mean when we use that term limiting reactant. All right, so I'm going to let you guys take a break, and when we come back, we're going to do lab 7.2 in the book, which is going to highlight this concept of limiting reactant. Okay? All right, you guys take a break.